Guys, today, of course, we're gonna work on the very last lesson. We're gonna be working on chapter 19, which is lesson 19.6. Now, we are going to talk about a different topic, which is not exactly related to probability, but it is usually connected to the idea of arrangements and how we organize items to be able to get all the possibilities depending on the components of each arrangement. Okay. Now we are going to talk about permutation. Sorry, I wrote it down in Spanish. My bad. And combination. What is permutation and what is combination? Both of them are just ways to arrange items. Now, I need to keep in mind that every time I do a permutation, I need to keep in mind the order. That means that if I want to make a permutation and I have the letters L, O, V, E, that is an arrangement, right? But I can also have E, L, O, V, and that would be another arrangement. Now, because the letters are in a different order, I can count these two as different arrangements. All right? So here we talk about permutations. All right? Where order is actually important. Now think about these letters. I know. I have 5 letters, right? And then those 5 letters, if I change the order of the letters, like for instance, I can say, right? Then I'm changing the order of the letters. But since I'm using the same 5 letters, this is not going to be counted as a different arrangement when I'm talking about a combination. All right? So every time I think about a combination, the order is never going to matter as far as I want to get an arrangement with all 5 letters. Okay? Now, I could probably have a different arrangement, like out of these 5 letters, I'm going to make arrangements of only 3 letters. So this is a combination. But if I change it to 3-letter arrangements, then I can have, this is 1, right? And then I can have this another one. So those 2 are going to be different arrangements because I'm using less letters that I was given. But if I'm using the same 5 letters in a different order, I cannot count it as different. Those 2 are going to be the same. And that's what combinations do. They do not care about the order. When I have less and I start having different letters, even though I'm changing only 1 letter, then it's going to be counted as a different arrangement. All right? Now think about permutation and combinations in specific contexts. For instance, if I want to think about permutations as, for instance, think about a locker lock. If I have a locker lock which needs a code, then the code has to have, I don't know, let's say 4 digits, right? If those 4 digits, this is a locker lock code. Now those 4 digits can be only odd digits. So I know I only have options, right? 1, 3, 5, 7, and 9. I don't have any more options. But if I am talking about permutations here, then I need to keep in mind one thing. And that is that if I decide to put the 1 here, then I need to be careful with the order. And if I'm actually allowed to have repeated digits. Can I have repeated digits? Well, we don't know, right? If we can have repeated digits, then I would actually be able to, or to have one here and here and here, right? That's an option. But how about no repeated digits? If I don't have the chance to have the repeated digits, then I know if one is here, it's never gonna be allowed to be here, right? So that's why we use the fundamental counting principle. We know we have actually how many options? 1, 3, 5, and 7. Now 1, 3, 5, and 7, it's actually, well, and 9, right? That's 5 options. If I am not allowed no repeated digits allowed, then I need to keep in mind that 1 is going to be there and I cannot use it any other way. So here in the first place, I actually have 5 options to use, right? But once I use this option over here, because of the order, I am not going to have the same options here. So I'm going to have 1 less. And here I'm going to have 1 less. And here I'm going to have 1 less. So I'm going to end up with a fundamental counting principle. 5 options times 4 options times 3 options times 2 options. Once I do that, then I know I'm going to actually get 20 times 6, that's 120. I have 120 possible codes I can use for my lock. And so that, as of course a lot of codes I can use, but then it's because of the order. The order matters here, all right? Now, when we talk about permutations, everything that implies order, for instance, making a line. If I need to make a line and I have 10 people to make a line for lunch, then how many ways can I arrange the people, those people, to actually make the line? If I decide the first person just to stay there, then that person cannot be at the same time in the 8th place, right? That person got to be in the first place and wait for lunch. What that means is that I had 10 people at the beginning and anybody could take the first place. But once it is taken, then for the second place, there is only 9 people who can take it, right? And for the third place, there's only 8 people who can take it, and so on. So I would actually end up having, if I want to make 10 people to make a line, then I would have to think about, yes, I have 10 options in the first place. Then I have 9 options. Then I have 8 options. Then I have 7 options, 6 options, 5 options, 4, 3, 2, and 1. Okay? So now what that tells us is that of course the last person is not going to have any chance to choose. We know that. But it's because the order matters. So this is permutation. This is permutation. Okay? Now permutations work, if you think about it, permutations actually work with factorials. What is factorial? Factorial is somehow related to fundamental counting principle, but it's not the same. Why is not the same? It is related because it is also a product, right? But here, the factorial is going to be the product of all positive integers less than the number I'm using. So I'm sorry, so here, if I want to use 10 people, and then I want to know how many options do I have, I'm going to use 10 factorial, which is 10 times 9 times 8 times 7 times 6 times 4 times 5 times 4 times 3 times 2 times 1. That's what a factorial is. And so that is going to allow us to find the permutations easier. If we come back to the word love or Janice, right? if they ask me how many words, whether they make sense or not, can you make out of those 5 letters? How many words, whether they make sense or not, can you make out of those 5 letters? Well, I'm gonna have 5 spots, right? And then of course here I have the 5 options, all 5 letters. But once I take one, I only have one less here, which is 4, and then one less here, and one less here, and one less here. So if you think about it, this is 5 factorial. Why? Because it's the product of all possible integers less than the number. 5 factorial, 5 times 4 times 3 times 2 times 1. And again, I'm gonna have 120, isn't it? 20 times 6. So that it's what permutations allows us to do. Now combinations, it's different because combinations that does not care about the order. The order is not important. What that means is that as far as I make it for whatever category they decide to create, I'm fine. For instance, so say we're getting a group to go into a math contest to a different school. And we have 6 spots out of the 35 we are. So you are going to try to get 1 spot, right? But if you try to get 1 spot, it doesn't matter whether you're chosen first or last, as far as you're chosen and you get to go to the contest. That's what combinations do. You are actually able to make it to the group we're getting out of the total. If you are able to make it to the group, then that's what really matters. It doesn't matter whether you're the first, the second, or the third. What you really want to do is just to be part of that small group that is taken from the total of items that you're given, okay? So combination, we're always gonna think about combination as with this formula, all right? Now permutation also uses a formula, but it's just easier to think about factorials. It's just easier that way. Combination is pretty simple. Every time we want to combine, we need to make sure that we need a total of objects in the set, which is going to be n, now n factorial, so keep in mind the product, right? And we need the number of objects that is going to have the smaller group we want to get out of the total, or that are going to be selected from the set. And it's also going to be in terms of factorials. If we understand that, let's just come back to the example. For instance, we're gonna make a committee. So we have 6 students, right? And we wanna make a committee with 4 students. Now, how many, so this is the committee, right? Now, how many, I'm not sure if committee is actually well spelled, but you can check out at home. Now, how many different groups of students can we get to form the committees with those 6 students? That is combinations. Why? Because as far as I make it to the committee, it doesn't matter if they choose me first, second, third, or fourth. I just want to make it to the committee, all right? And how is the formula going to work? Well, the total is going to get combined into the group. So 6 combined into 4. And I know it's going to be 6 factorial up here. And then I'm going to have 4 factorial times 6 minus 4 factorial. Now, of course, what that means is 6 factorial up. Now 4 factorial, and 6 minus 4 is 2 factorial. Now please remember what 6 factorial means, right? It's the product of all the integers less than 6. So it's gonna be 6 times 5 times 4 times 3 times 2 times 1. So I need to think about 6 times 4 times 3, times 5. And you know what? I'm just gonna leave it in 4 factorial. For only one reason, I'm going to show you right now. 4 factorial and 2 factorial. Well, 4 factorial and 4 factorial, and we have a product, so we know we can cancel this out, right? So what that means is that I have 30 up here, and then 2 factorial will be actually what? 2 factorial is equal to 2 times 1, which is 2. So we know this is actually 15. So we have 15 ways, 15 different combinations of students, of these 6 students, to get committees with 4 students. All right? That's what a combination is about. I don't care about the order. I only care about getting into the small group I'm taking from the total number of objects or items in the set. All right? I'm going to do some exercises with you from the lesson, and that's probably going to help us understand a little bit more. Let's see. Now, problem 1, if you think about problem 1, it says choose 2 people from 3. Now, question, am I able to think about order? Not really. I need 3 people. I have 3 people, but I need 2 people. Whether I'm the first or the second person in the pair, doesn't matter. So the order doesn't matter. And because the order doesn't matter, then I gotta think about combinations. So I'm gonna do 3, which is the total, combined into 2, which is the small group. So 3 factorial times 2 factorial, divided into 2 factorial times 3 minus 2, and that is 3 factorial over 2 factorial, and this is gonna be times 1 factorial. All right? Now, of course, 1 factorial is 1. We know that. We're never gonna use 0, because if we use 0, then everything's gonna be messed up, right? And here I'm gonna have 3 times 2 times 1. And here I have 2 times 1 times 1. So I can cancel things out, see? And I know 3 divided in 1 is actually 3. Isn't it? So that's what my answer is going to be. I have 3 possible pairs of 2 people, if I choose from 3 people I had at the beginning. That's it. Now, let's think about problem number 2. Problem number 2 says you gotta choose now 3 people from 4 people. Again, does the order matter? Not really. Not really. I wanna make it to the smaller group. Doesn't matter how. So, it's gonna be 4 combined into 3. 4 factorial divided into 3 factorial times 4 minus 3, and that's gonna be 4 factorial divided into 3 factorial times 1 factorial. And just not to make it so complicated, I'm just gonna go until 3 factorial so I can cancel things out. And this is gonna be canceled just because they both have factorials. Careful with canceling the same thing, all right? And we know 1 factorial is actually 1, so that's gonna be 4. So my answer is gonna be 4 different groups of 3 people out of those 4 people they gave me. That's simple, all right? Let's do some exercises in regards of combinations. Now combinations, in regards of permutations. So think about number 3. Now what they're asking you is how many arrangements can you make out of the letters B, A, T? Whether they make sense or not. Now here the order is going to matter. Why? Because if I have this arrangement, right? Or if I have this arrangement, those are going to be different arrangements. And so I gotta be careful with the order, right? Now remember, I have 3 spots. And I know, just like the line, in the first spot I have 3 options, all 3 letters, right? But then in the second spot I only have 2 options because I already chose 1 in the first. And finally, for the last spot, I'm just gonna have 1 option. So what I'm getting here is actually 6 possible arrangements or permutations when I have those 3 letters, okay? It's that simple. Now think about problem number 4. If we think about problem number 4, now we have the words CK, which is sec. How many permutations or arrangements of letters can I make, whether they make sense or not? Now, if we think about it, again, we can just say, you know what, this is another arrangement, and the order is different, so it matters. But I'm not gonna do the entire list, because lists take a lot of time. I'm trying to teach you how to deal with combinations and permutations without making lists, because it's just too long. It takes too long. So here we have 4 spots, 1, 2, 3, and 4. Now again, for the first spot, I have 4 options. But for the second spot, I have 3 options. And for the third spot, I only have 2 options. And for the last spot, I'm always gonna have 1 option. If we multiply this, it's gonna be 24, isn't it? So we have 24 here. That is our answer, all right? That is for the word sack. And the last word they have over here is beauty. Which is all these words. If you look at it, 1, 2, 3, 4, 5, and 6. I have 6 options, then 5, then 4, then 3, then 2, then 1. Why? Because of the order. And that, of course, is going to be a whole lot. So 3 times 4 is going to be 120. 120 times 6 is going to be 720. So we have 720 different arrangements we can get out of this, these 6 letters, all right? That's pretty simple. Now, in terms of the problems, just think about what I just told you. Am I trying to get order in the arrangements? Is it very important to keep order? Or is it only a matter of being part of the smaller group and that's it? If it is only a matter of being part of the smaller group, then I need a combination. If order is important, then I know I need a permutation. That's it, all right? I will see you down Friday to work on questions you might have. Bye.